Today we have Kalman Filter. It's used for tracing of any kind of movements of any objects. When we have perfect measurements of the position, for example, but it's noisy, and the Kalman Filter predicts a position based on noisy sensor readings and our prediction calculations. Kalman Filter assumes a normal distribution of all the noises. Kalman Filter uses sensor readings and our prediction to estimate current position. So if we have, for example, sensor reading saying that we are somewhere here, let's think this graph refers to some position in space. Yep, so sensor reading tells us we are somewhere here in this point and in some space around, because it's normal distribution. And our prediction, so how we have calculated where we are, and our calculations tell that we're somewhere here in this space. Then the Kalman filter will estimate our position somewhere in between by some mathematical formulas. So new estimated state in Kalman filter will be later refined. Is calculated by prediction matrix, for example, some physics, known physics. Previous estimated state, it's x hat k minus 1, and some control matrix multiplied by control vector. It means the change in physics. For example, we are train driver and we are trying to calculate our next position. To do that, we know that there is some physics behind, and we can affect the movement of our train by, for example, moving the lever and making higher speed for the train. The control vector shows the measure of how much we have moved our lever to make our train move faster, and control matrix shows the physics behind. So the new estimate is a prediction made from the previous best estimate plus a correction for known external influences. Control matrix shows us the external influences. We also calculate the uncertainty of the estimate. Covariance matrix pk shows the uncertainty. The uncertainty is predicted from the old uncertainty with some additional uncertainty from the environment. The new estimate is not final. We have to refine it using the measurements that we took. So we refine the estimate. K is Kalman gain. We give the information more weight if the measurements have very low uncertainty. If the movements are very uncertain, it will give the innovation less weight and rely more on the estimate. Some words about innovation, it's ZK. It's how accurate the estimate described the measurements. If very bad, the innovation is very high and will correct the estimate more. If very good, the innovation is small and will not correct much. Actually, it's just the difference between estimate and measurements. What's HK? It's observation matrix. It's needed when sensor readings and state measurements. So Kalman gain gives more weight to sensor readings or our measurements depending on the uncertainty of them. More uncertainty, less weight. Less uncertainty, more weight.